So under ignorability, we talked about the extrapolation distribution. And that really just comes out to be z, the unobserved part of z conditioned on the observed part and the covariates. So this is sort of the justification for multiple imputation in the sense that you can just predict from this model and impute the missing data. And then you can conduct a full data analysis. So the classical way to impute the data set is via Bayesian proper imputation. And another way is to use multiple imputation via chain equations. So it's called Bayesian proper imputation, but then the Bayesians think it's an approximation to a proper Bayesian procedure, which would be the last equation there. Like that's proper Bayesian procedure, but multiple imputation is an approximation to it. And I'll tell you why it's called Bayesian proper imputation. But if you can already get at the parameters of interest, I don't necessarily see the point of wanting to impute your data set. But if you are a statistician and you want to hand the data off to other people, this is extremely valuable because instead of having them do likelihood analysis, you can say, here, I imputed these data sets. You can do whatever analysis you want. And then we can put them together and take into account the variance for the parameters that you have. So this is more for a practical consideration. Whereas like if you just want to get at, say, the parameter of interest, which would be gamma, because that indexes the full model for the data, then you probably wouldn't do this. So the Bayesian proper multiple imputation. This is proposed by Donald Rubin in a paper in 1987. And basically what he wants to do is from each missing value in the data set, you would impute it m times and to create m different data sets. Like we talked about single imputation where you don't only create one, but in multiple you want to create m different ones. And you would then analyze each data set as if all of the observations were observed, and then you would pool them together to take into account the variation within the initial estimates that you start with. So the reason it's called Bayesian imputation is because what you first do is you draw from the posterior distribution of theta given the observed data. So you posit a model, and then you can draw from that model a theta m. So in essence, like what you could do is there's also improper imputation and sort of proper imputation, where in improper imputation you would just have your primary estimate theta hat, and you would just impute multiple data sets based on that. But here, if I get at the posterior distribution of theta, given R and the observed data, there's still, to me, like this is more intuitive because there's still uncertainty about what theta actually is. So now if I take m draws from theta, and then draw from the predictive distribution indexed by the theta to the m, that's going to give me more variation, which would make me feel more comfortable with what I'm doing. So after you draw theta m, you impute the missing values by predicting the missing part of z conditional on the observed part and the theta that you drew from your predictive or posterior distribution. So the estimator for theta, so like this is a approximation to a Bayesian analysis. So the estimator here would be just the average of the estimates that you get for each data set. Make sense? Questions? All right. So a classical way of doing multiple imputation has been to just assume that everything is multivariate normal and just impute based on that. So even if you have binary variables, like if you have 1, 0, what they do is just take the mean of it and impute decimal places into a known to be categorical variable. So supposedly that works, but that necessarily doesn't have the intuitive appeal as multiple imputation by chain equations. So now instead of z just being one variable, let's assume that within z there's y sub 1 through y sub k. And this approach was not that old. It was proposed in 2007 by Van Buren, and he has a paper in JSS for a package he wrote for R called mice, which I'll just talk about in a bit. So this is also sort of ad hoc in the sense that, filling it in as a normal distribution seems incorrect, obviously, but this also starts off with what you do is for all of the missingness patterns within each variable, you would initialize the data set by say if y sub ik is missing for a person, so yk is missing for person 1, then you would sample from where, like, the YKs where they've been observed. So if YK has been observed for 2 through 5, you would take one random one and impute it as into the value for Y1. So you do that for all of the variables in your data set, and then you just arbitrarily pick any variable you want, and then you regress it on all of the other variables. And you can do multiple types. I mean, if it's a categorical variable, you can use logistic. If it's ordinal, there are things for that. If it's just a continuous, then you can use a regression. So you would regress. You would take the complete cases of where it was actually observed. So despite the fact that you imputed all of them, you would only use the subset of data where Y1 was observed. And then you'd regress all of that on all of the other variables, find estimates. Then you would use those estimates to predict Y1 for where it wasn't observed. And now you'd go to Y2. And you'd do that. You'd do the same thing. You'd find the Y2s which were observed initially, and you'd regress it on all other variables, including Y1. And then you'd continue cycle that through each variable. And you repeat this through 10 to 20 cycles. So one cycle would be you cycle through Y1 through 5 YK, and you do that 10 to 20 times to stabilize the data set. And so you do this once, and you get the 10 to 20 cycles. That's one imputed data set. You do it m times to get the m imputed data sets like we had earlier in the previous slide. So the order of variables in which you do the regressions are really important. Supposedly answers change if you change the order, which is not ideal, obviously. And what's funny about this is that, I think I might have it on the next slide, but yeah. So all of these things supposedly work well in practice. I haven't done, it would be interesting to see how well they actually do work. Okay, go ahead.
How does this relate to sequential regression imputation? Because that's mice as well, which Raghunathan, I think out of Michigan, came up with. And I thought they always say to do it, you start with least missingness and go to most missingness in terms of the order in which they do with the sequential regression imputation. I was just curious. That came up in your strict, because I always thought this was called, I never heard the chain equation. Kind of means the same thing, it sounds like.
Yeah, I haven't heard of that, but I mean, on some level, you could even. The thing is, like, it would be weird to have you start with the least missingness one, but there are going to be arbitrary missingness within the variable. So you could have, even with 1,000, if you have enough predictors, you could maybe only have 1 or 2 complete cases where you could do the regression on, right?
Well, that's what they do in that paper at the start. Although they have ideal situations that would leave you at least 50% of the data of the predictors.
Okay.
It's like you said, things in practice. They have a lot of.
Yeah.
I was just curious how that related. Say that's only early 2000s. It was something related to like a census data that they were imputing.
Honestly, it's something that I've just heard of the first time, but so yeah, the order of variables is really important in this. So I don't have examples with particular software, but you guys should just reference Dr. Davidian's site, because anything that I would do would not compare to the quality of code that she has up on her website. So there are packages in both R and SAS, or packages and procedures to be SAS savvy to conduct these analysis. And proc-MI and proc-MI analyze in SAS are 2 pretty good procs that you can use relatively quickly, because it's much more, like R takes a lot more time to do all of these things. Well, you can, that can be your 10,000 citation paper is mice for Julia. So Van Buren, the person who came up with this, has a paper in JSS outlining the mice package. So what's cool about it is that you can do like regression trees for classification and prediction for continuous. You can use LDA, you can do logistic. It just depends on the type of variable that you have. He gives you a lot of options that you can potentially use. Also, something that should be noted is that if you do mice using the R package and if you do mice using proc-MI, you will probably get different answers. And no one knows why. supposedly everyone knows that you'll get different answers, but no one's like done the research to understand why you will get different answers. So basically this whole talk is going to be careful about what you're doing in general. So I only have a few more slides left. So if data are not ignorable, it's just called non-ignorable missingness. So if ignorability is violated, you'll get into the realm of non-ignorable missingness. And that becomes much more complicated because you have to use pattern mixture models. So I'll just do like a quick overview of this in a couple of slides, and if it's something of interest to you and you see that in your work, you can again refer to Dr. Davidian's notes or literature. So in this situation, you'd want to use the pattern mixture factorization. Here, like if you have non-ignorable missingness, the full data model has to be specified. You just can't ignore the missing data that you have, because in the ignorability assumption, when it was met, the parameter of interest gamma was we could find the posterior distribution of it with the observed data, so we ignored the missing data. And here you can't really do that. You have to make assumptions about it. And the extrapolation distribution with which you do multiple imputation is not identifiable unless you make really strong assumptions. So you can make assumptions that obviously aren't going to be verified. You can make modeling assumptions. You can put informative priors on parameters which are going to index that distribution. So if you think that, like if you know that the parameters are going to be in a certain range, you can just draw based on that. So under the pattern mixture factorization, the joint distribution of the full data can be factorized as this. So you have this part right here is identified from the actual data that you observe, because that's just the distribution of the observed data given R and then the probability of missingness. But there is the extrapolation distribution which you can't necessarily identify. So you have to make assumptions about it to get the full joint model. There are many different assumptions that you can make, and they're all ad hoc in some ways. And one of the assumptions is that the complete case missing values are, and where it means that the density for the missing part of Z is the same as the density for the observed data. And other assumptions that you can make are available case and neighboring case missing values. But none of these assumptions are verifiable from the data that you observe. So in summary, obviously missing data should not be ignored. Like you should not just do complete case analysis if 50% of your data is missing. Unless you can justify missing completely at random, which you probably won't be able to justify anyways because all of those assumptions are not justifiable from the data that you observe. So like I said, in the biostatistics field now, the recommendation from the FDA, I think, is that you assume missing at random and you do a sensitivity analysis. So like I said, strong unverified assumptions are required. Priors clearly incorporate these assumptions as part of the model. So I guess this is a strength of the Bayesian framework, where whatever prior you bring in is going to be part of the model that you're going to use, versus in the frequentist paradigm where, I mean, they look down on Bayesians for being subjective, but you're going to have those same assumptions, but you're going to have to like justify them in different ways. But here you can just incorporate them in the model. And also you can include other information that you have about the parameters of interest, and that'll make your parameters more identifiable. Multiple imputation methods can be used to fill in the data, but you should do it properly because there's variance between, so every time you draw a theta m from the posterior distribution given the observed data, there's variance between the theta draws that you have, and all of your estimates are going to be different. So there's variance of the estimator, and there's variance within the estimates that you initially get. And like I said, different methods that you use will lead to different conclusions. So I guess I don't necessarily have a recommendation of what to do, but because I feel like no one does, but different methods will lead to different conclusions. And this is a very case-by-case subject where you try to figure out what you can do best, and you just do it because you don't really have another choice, because you can't just throw out data or just do complete case analyses. So this is all I have. Does anyone have questions?
You go back one. You didn't start on this long enough, but okay, you've got pattern mixture factorization, but you're title says mixture models, and maybe I'm not seeing it, but I mean, mixture models are a very explicit term.
Well, if you,
I'm not seeing where the mixture model.
If you integrate out the missingness,
yeah.
like, so it goes into measure theory, which I don't know anything about, I think.
Yeah.
But if you integrate that out, then what you're doing is the probability of a particular missingness pattern, like you're summing over that. So the probability of this being observed.
Different components based on their missingness.
Yeah.
So it basically is like a two-component mixture model.
Mm-hmm. I mean, I don't know much about
Okay,
mixture
okay.
models. Sorry.
Okay.
But there is like if you integrate that out, it turns, like you're summing over the probabilities of missingness.
Okay. All right. So, I just didn't see the explicit mixture model setup. But
Okay.
So if you do the fully Bayesian imputation stuff, do you only need single imputation, or do you still do multiple?
You'd want to probably do multiple imputation. Well, the thing is, it depends on what you mean by fully Bayesian imputation, because everyone's argues, or it seems people aren't completely in agreement with that. Like multiple imputation, according to Rubin, it's Bayesian because you're drawing from the posterior distribution at first, but then you're doing like a likelihood analysis. So the Bayesians will say, or the Bayesian that I read, who wrote this paper, says the multiple imputation is an approximation to a Bayesian procedure under ignorability, which where you can just get the posterior distribution of the parameters of interest. I feel like you should never really, intuitively, you should never only impute the data set once, because the appeal of multiple imputation is the fact that, yes, I have an estimate for theta based on the data I observe, but I don't know what it actually is. And I'm not comfortable with positing or saying that this data, the estimate, based on the data I observed, actually applies to the data that I didn't. So now you're including another level of variability. So you're drawing from that posterior distribution, and you're saying, let me vary with different data and draw based on that and see what the result is. But it would be interesting to see, like, if you made credible sets, how often with single imputation and multiple imputation they would actually meet or contain the true value. Supposedly they do a good job.
You said that sometimes when you think at random and completely at random, you gotta assume missing at random and do a sensitivity analysis.
No. If you assume missing at random, then you can compare between the two. The the FDA says you, in an analysis, like in a regular like clinical trial, you assume missing at random and then do a sensitivity analysis to missing at random, whether or not it's true.
Okay.
So
I was just thinking, conceptually, I kind of think of that sort of as like a holistic model. I didn't know if you came across, I guess it's hard to test something if you don't actually test data, but I don't know if you came across something like a formal way to
yeah, I mean, there's the things you're interested in testing. Yeah, like you said, you don't have to observe the data. So that's why, I mean, you can always bring in prior information, and that's where it's really powerful, if you really understand what's going on and the mechanism behind the data generating process.
Out of curiosity, what is Dr. debate like to run through what the FDA does? What if it is extremely sensitive, or they think it's the not missing random sheet? What do they do when you spent millions of dollars on a clinical trial or whatever?
Well, I mean, the FDA's first recommendation was make sure you don't have missing data. And then if you do this, and then it's probably a case-by-case basis. I can't see.
Dr. Did any do any intuition help play any insight into that?
No. I mean, her whole thing also was just like, we're just doing the best we can. Like, we can't verify any assumptions we make. Some of them are principled under certain assumptions, but again, they can't be verified. So.
Also, there's the Bellman has a package, right? MI, LN, is an R package.
Yeah, there is a package for multiple imputation besides mice in R. It's probably MI.
By Bellman, I don't know any at all.
He's probably just doing proper. He might be doing proper imputation.
You're getting all that sequential regression.
stand? I imagine it uses it. Is it pre-stand or post-stand at this time?
Use it once in the forever and ever actually ran.
I think like proc MI is pretty good. I liked it. I'm recommending SAS. I never thought I'd do that, but it's pretty fast and
Mice code is fast as well, right?
yeah. So proc MI actually can also do mice. So
Is that
yeah,
integrated?
yeah. So you can also posit different models for the missing variables. But, I mean, to me, not assuming everything is multivariate normal is very appealing, relatively. So mice intuitively makes the most sense because you're leveraging information across all the variables that you have.
I will also recommend that. I just did some imputation in undergraduate report test where you're doing like imputing value online, and we also have constants and everything. So we have that category of variables and then some other categories. And they were able to use it and show them exactly like, pretty much everything. I don't think they understand the full machine design of it.
Yeah. I mean, but unfortunately for being so expensive, SAS's documentation isn't as good as it should be. And it's yeah, that's also true. But like I feel like in a lot of things they try to go into the theory behind it versus like actually laying out what needs to be done. Yeah, I'm standing in SAS Hall.
No, you're an employer.
All right. Well, if no one has any more questions.